Swayam Prabha. Digital India. Educated India.
Hello students, welcome to today's lecture. In the last lecture, we discussed about the angular momentum operator. To refresh your memory, we saw that the angular momentum operator would have three components Lx, Ly and Lz, and these three operators Lx, Ly, Lz, they do not commute with each other. Whereas, we defined L square operator, which was the sum of Lx square, Ly square and Lz square. This L square operator on the other hand commutes with Lx, Ly and Lz operator. So, these commutation relations are quite important in discussing the properties of angular momentum operators and their eigenfunctions and eigenvalues. We know that when two operators commute with each other, they have common complete set of eigenfunctions if these two operators are quantum mechanical operators and therefore, they are Hermitian operators. But if two Hermitian operators they do not commute with each other, we cannot simultaneously observe the outcome of their we cannot simultaneously observe the outcome of an experiment when we try to measure both these operators, and with the precise determination of their eigenvalues is forbidden by uncertainty principle. There would always be some uncertainty in one of these observables. However, on the other hand, when they commute, we can have a common complete set of eigenfunctions for these two operators. So, therefore, we cannot simultaneously determine the value of Lx, Ly or Lx, Lz or Ly or Lz, whereas we can determine simultaneously and precisely the value of either L square or Lz, L square and Ly or L square or Lx. So, we have to make a choice. Now, what we would do is that we would see that we would say that okay, since L square and Lz commute, we try to find the eigenfunctions of L square operator and Lz operator. In fact, we will try to find out the set of eigenfunctions which are simultaneously eigenfunctions of L square operator and Lz operator. These eigenfunctions, however, are not going to be eigenfunctions of Lx and Ly operators. Why? Because since they are Lz operators eigenfunctions, they cannot be eigenfunctions of Lx operator and Ly operator, because Lx and Ly they do not commute with each other. So, this will keep in mind and continue our discussion as to how we can get simultaneous eigenfunction of L square and Lz operator. The discussion that we would carry forward is by taking L square and Lz as the two operators whose eigenfunctions we want to evaluate, but we could have also done the same thing for L square Lx or L square Ly, because since they also commute, we can also design a common complete set of eigenfunctions for these two operators. However, to follow convention, we will stick to L square and Lz operator. To do this discussion, let us define. So, let us define psi alpha beta as the eigenfunction of L square and Lz operator. So, this psi alpha beta are the simultaneous eigenfunctions of L square operator and Lz operator. So, you see I have used two indices to define my eigenfunctions alpha and beta. That is because these eigenfunctions are going to be eigenfunctions of two different operators. So, therefore, it would be easy for me to monitor the two operators eigenfunction by two indices. So, I define that if I apply L square operator on this eigenfunction, I would get something like this alpha square h bar square psi alpha beta. So, this relation tells me that psi alpha beta is an eigenfunction of L square operator with the eigenvalue of alpha square h bar square. You would be wondering, why did I choose this way of defining my eigenvalues? Mind you, I still do not know what is alpha, but if I look here L square, you would see that the dimensionality of angular momentum matches with that of the Planck's constant h. So, to have an analogy between the operator and the corresponding eigenvalue, so I defined this h bar square which would take care of the dimensionality of the problem, that would leave out this alpha square, which will be a dimensionless quantity. I still do not know what this alpha is. I similarly define when I act LZ operator on psi alpha beta, I get beta h bar psi alpha beta. Again, since L operator has dimensionality of the angular momentum operator has dimensionality of h or h bar, I am defining this eigenvalue as beta h bar such that beta is a dimensionless quantity. It can be any other real number. So, these are still my definitions. I still do not know what is alpha, what is beta. I am just trying out, I am just defining if my psi alpha beta is a simultaneous eigenfunction of L square operator and LZ operator, and these would be the eigenvalues where I still have to determine what alpha and beta are. Now, before I do this, go further, let me evaluate this relation. L square minus LZ square operator. When this operator acts on psi alpha beta, what would I get? I know psi alpha beta is an eigenfunction of L square operator. I also know that psi alpha beta is an eigenfunction of LZ operator. Now, when I apply L square operator on psi alpha beta, I get alpha square h bar square. When I apply LZ operator on psi alpha beta, I would get beta h bar. So, when I apply this operator twice, LZ and then LZ on this psi alpha beta, I would get beta square h bar square psi alpha beta. So, we see that psi alpha beta is not only, if I define psi alpha beta as an eigenfunction of L square operator and LZ operator, this is also turning out to be an eigenfunction of L square minus LZ square operator. And what is the eigenvalue? The eigenvalue is alpha square h bar square minus beta square h bar square. But when I look at this operator, I know that L square minus LZ square is simply Lx square plus Ly square. So, this eigenvalue is actually the eigenvalue of Lx square plus Ly square operator. I know Lx is a Hermitian operator, I know Ly is a Hermitian operator. I also know since Lx and Ly are Hermitian operators, their eigenvalues are going to be real. They may be positive or negative for Lx or for Ly. Now, if Lx and Ly's eigenvalues are going to be real, Lx square and Ly square's eigenvalues are going to be real and positive. So, therefore, this eigenvalue alpha square h bar square minus beta square h bar square is going to be real and positive. So, therefore, alpha square minus beta square is going to be greater than or equal to 0, and therefore, alpha square is greater than or equal to beta square. I started defining alpha and beta. I did not know anything more about them, but now I see that this alpha and beta, the way I have defined, they follow a relation among themselves, that alpha square must be always greater than or it can be equal to beta square. When this relation holds, I can actually write down that beta is greater than or equal to minus alpha or less than or equal to plus alpha. This you can verify by taking a small example. For example, if you take 5 square is greater than 4 square. So, therefore, 4 will be greater than minus 5, but it will be less than plus 5. So, this relation between alpha and beta is something that we are getting from the way we have defined this problem. We will remember this relation and we will come back to this relation after a few moments. But before that, what we will do is that we will look at a new function when I am applying my L plus operator on this eigenfunction psi alpha beta that I have defined as the simultaneous eigenfunction of L square and Lz operators. So, when I apply L plus operator on psi alpha beta, of course, this is an operator. I do not know whether this is an eigenfunction of this L plus operator or not. rather since L plus and Lz they do not commute. So, therefore, this is psi alpha beta is certainly not an eigenfunction of this. So, therefore, this is a function. When this operator acts on this function, I will get some other function. So, this is the action of L plus operator on psi alpha beta gives me another function. So, I would see what would I get when I apply my Lz operator on this new function, that is L plus psi alpha beta. So, Lz, I am making a measurement of Lz operator on this new function, and how do I get this function? Well, I get this function by applying L plus operator on the psi alpha beta. What is psi alpha beta? Psi alpha beta is the eigenfunction of L square and Lz operator, and I have defined them already. So, I see that I have Lz and L plus. I know from my previous class Lz and L plus they do not commute, rather the commutator between Lz and L plus is so, therefore, Lz plus L plus minus L plus Lz will be h bar L plus. So, therefore, I am writing down Lz L plus as L plus Lz plus h bar L plus psi alpha beta. I used this commutation relation to write Lz L plus as L plus Lz plus h bar L plus. Now, I see that this operator Lz operator is now in the right hand side. So, it can act on this function, and where this function I know is an eigenfunction of Lz operator with an value of beta h bar, and I bring that out, and I am left with L plus operator on psi alpha beta plus I have h bar L plus psi alpha beta, and I can simplify this as beta plus 1 h bar L plus psi alpha beta. So, I see in the left hand side and in the right hand side I have, what am I doing? I am trying to see an action of Lz operator on this function L plus psi alpha beta. I see that this function L plus psi alpha beta is an eigenfunction of Lz operator with the eigenvalue beta plus 1 h bar. If psi alpha beta is an eigenfunction of Lz operator, then L plus psi alpha beta is also an eigenfunction of Lz operator with an eigenvalue of beta plus 1 h bar. So, this is what I obtained from this relation. Alright. Now, what I will do is that I will see what am I getting when I make measurement of L square on this function. So, L square when I apply on psi alpha beta, what would be the outcome? So, I see I can show that L square and L plus they commute. I know L square and Lx commute, L square and Ly commute. So, therefore, since L plus is Lx plus I Ly, so therefore, L square would also commute with L plus. Since L square commutes with L plus, I can simply write this as L plus L square. L square psi alpha beta. Now, I see this L square operator is in the right hand side. So, it can act on psi alpha beta function, and I already know psi alpha beta is an eigenfunction of L square operator with an eigenvalue of alpha square h bar square, and then I am left with L plus on psi alpha beta. Again, when I look at the left hand side and right hand side, I see that this function L plus psi alpha beta is an eigenfunction of L square operator with an eigenvalue, it should be h bar square. So, with an eigenvalue of alpha square h bar square. So, I see that if I have defined psi alpha beta as an eigenfunction of both L square operator and Lz operator, then L plus psi alpha beta is also an eigenfunction of Lz operator with an eigenvalue of beta plus 1 h bar, this function is also an eigenfunction of L square operator with alpha square h bar square as the eigenvalue. So, now since I am in the process of finding the eigenfunctions which simultaneous eigenfunctions of L square and Lz operator, I see that this L plus I alpha beta function satisfies the requirement, because I see that it is a function which is a simultaneously eigenfunction of L square operator and Lz operator. So, therefore, this is L plus I alpha beta is one of my possible eigenfunctions that I am looking for. One thing that you would notice is that this particular functions L plus I alpha beta, when it, what will be the eigenvalue when I make apply Lz operator? The eigenvalue is simply beta plus 1. So, the beta index increases by 1, whereas the alpha index remains as it is. So, I started with my psi alpha beta function, I defined this as the eigenfunction of L square and Lz operator, where alpha square h bar square was the eigenvalue of L square operator and beta h bar was the eigenfunction of Lz operator. Now, I am coming to a place where L plus psi alpha beta is also an eigenfunction of Lz and L square operator, but in this case the eigenvalue corresponding to Lz operator is becoming beta plus 1 into h bar, but eigenvalue corresponding to L square operator remains as alpha square h bar square. So, therefore, I am going to write this function as a new function psi alpha beta plus 1. So, this function which is another eigenfunction of my Lz and L square operator has two indices. Instead of having alpha and beta, I am having these indices as alpha and beta plus 1. This should remind us that when this function when I apply Lz operator on this function, I will get beta plus 1 h bar as the eigenvalue. When I apply L square operator on this function, I will get alpha square h bar square as the eigenvalue. So, what I have done is that starting from by defining one eigenfunction of this L square and Lz operator, I have come to a point where I can find out another eigenfunction of these two operators. And how did I get that? I obtained that by using this L plus operator. Similarly, I can also show that, so this was my alpha psi alpha beta, and when I apply L plus operator on this, so I got another function which is psi alpha beta plus 1. I can also show when I apply L plus operator again on this function, I would get psi alpha beta plus 2 and so on. So, similarly, if I apply instead of L plus operator, if I had applied L minus operator, it is very easy to show. I would encourage you to do this exercise for yourself. You would see that when I apply L minus operator, I would get psi alpha beta minus 1, and one more time L minus operator would give me psi alpha beta minus 2. So, in this way what is happening is that starting from one definition of the eigenfunction and by repeated action of L plus and L minus operator, I am getting other eigenfunctions which are simultaneously eigenfunctions of L square operator and Lz operator. All these functions are eigenfunctions of L square operator with the same eigenvalue, that is alpha square h bar square, that is shown by this index alpha, which is not changing. But these functions are eigenfunctions of Lz operator with different eigenvalues. In this case, the eigenvalue will be beta plus 2 into h bar, this case it will be beta plus 1 into h bar, and this will be beta into h bar, and so on and so forth. So, here I see that starting from one eigenfunction, I can create all other eigenfunctions of L square and Lz operators together. So, similar to our harmonic oscillator problem, we can define this L plus or L minus as step up or step down or creation and annihilation operators. So, what we see here is that we have a large number of possible eigenfunctions. So, you can imagine I can go all the way down as far as I wish, or all the way up as far as I wish. Because alpha and beta, just to remind you, I still do not know much about alpha and beta, but something very important I already know about alpha and beta, that is beta is bound by two values, that it is between minus alpha and plus alpha. This is what we had already obtained. So, looking at this, it would say that I just, when I am obtaining beta, so I am going in the step of 1, beta, beta minus 1, beta minus 2, beta minus 3 and so on so forth, or beta, beta plus 1, beta plus 2, but it is not going to be an infinite series, rather it is going to be finite. Why? Because I see that the beta has an upper limit and has a lower limit. So, suppose let us define that beta has an upper limit, call this upper limit as beta max, and let us give a smaller name to it, I call it L. The maximum value of beta is L. Mind you, beta, this relation tells me that it can be equal to minus alpha or greater than, but whether it will be equal to minus alpha or little above minus alpha, I still do not know, but this boundary for this bound region for beta is something that I know. So, I am now defining this beta max as L. So, when beta is a beta max, the wave function, I will write as psi alpha, and beta max in place of L, beta max I am writing L. So, this is the maximum value of beta it can have. So, this is my eigenfunction, the uppermost eigenfunction. So, I have this psi alpha L, which is the uppermost eigenfunction. If I apply L plus operator on this, what would I get? Since L plus operator's action always takes the eigenfunction to the next eigenfunction. So, psi alpha would also be taken to psi alpha L will be taken to psi alpha L plus 1, but I know L is the maximum value of beta. So, therefore, there exists no other function above this. This is the upper bound. So, in this case, the action of L plus on psi alpha L should give me 0, and I will continue this by applying L minus before this. So, to evaluate this term, so this is again the right hand side is again going to be 0. Now, I look at L minus and L plus, I can rewrite this at L square minus Lz square minus h bar Lz. You can easily show by using the relation of expression for L minus and L plus, you would be able to come to this point. So, I have psi alpha L equals 0. So, when I apply L square on psi alpha L, I know psi alpha L is an eigenfunction of L square operator with eigenvalue of alpha square h bar square. When I apply Lz square on this function, this function is an eigenfunction of Lz operator with an eigenvalue of L h bar, because this is the place for beta. So, this I will get as L square h bar square minus h bar. When Lz acts on this psi alpha L, I will get L h bar psi alpha. So, when I look at this relation, this is the eigenfunction, of the non-trivial solution for this would be when this term, which are the eigenvalues, will be 0. So, therefore, alpha square is going to be L square plus L, or L into L plus 1. This is what I get alpha square and relation between alpha square and L. What is L? L is the maximum value of beta. I can similarly actually do by defining, let us define beta minimum as a new variable k. So, I said that there exists an upper bound, that is beta max, and there similarly there would exist a lower bound, and that I would call beta min. So, the function, the lowest function will become psi alpha k. If I apply L minus operator on psi alpha k, I would get 0, because L minus operator's action on any eigenfunction would be to bring the down to the next function. Since this is the lowest function, there is nothing below it. So, therefore, the action of L minus will be 0, and I would do L plus, I will apply L plus L minus on psi alpha k will be equal to 0. And if I continue, so I would show that L square, L plus L minus is L square minus L z square plus h bar L z on psi alpha k, which is 0, and when L square acts on psi alpha k, I get alpha square h bar square. When L z acts on psi alpha k, I get k square h bar square. When L z acts on psi alpha k, I get k h bar. So, you would see when you solve this, you would come to this point where alpha square is k into k minus 1. Now, what is k? K is the minimum value of beta. What is L? L is the maximum value of beta. Now, I see this alpha square is equal to L into L plus 1, and the same alpha square is also equal to k into k minus 1. So, therefore, I have this relation L into L plus 1 is equal to k into k minus 1. When I solve this equation, I would get L as minus k, that is one solution. Other solution I would get as L is k minus 1. So, please solve this, and then you would see that these are the two, just factorize this, and then you would see that these are the two outcomes. Look at this, L is k minus 1. L is actually the maximum value of beta, and k is the minimum value of beta. So, therefore, the maximum value cannot be 1 less than the minimum value. So, therefore, this is not an acceptable solution. So, I am left with only one solution, one possible solution, that is L equals minus k. So, what is L? Beta max. What is k? Beta min. So, this exercise tells me that I have beta max and beta min, where beta max is negative of beta min. So, and these beta values would be, the other possible beta values are obtained when I add, subtract bit 1 from beta max minus 1, or add 1 to beta minus beta min. So, now what I have is that for a given value of alpha, I have the eigenfunctions that are from beta max to minus beta min. So, just to summarize, so I had this psi alpha beta. So, where I said the maximum value of beta be L. So, therefore, this is my maximum value of beta L. If I have defined psi alpha L as the maximum value, the minimum value would turn out to be psi of minus L. And what are the other possible values? We saw that the eigenfunctions of the L square and L z operator were coming out in the step of plus 1 or minus 1 with respect to this beta value, or in this case this is L. So, the other values, other eigenfunctions are psi alpha L plus L minus 1, psi alpha L minus 2, and so on and so forth. So, here you see that I am starting from plus L and I am ending at minus L from in the step of 1. So, plus L or L minus 1, L minus 2, and I am ending at minus L. So, such a series where both plus L and minus L will appear and then they will be obtained in the step of 1, such a series is fulfilled only when L is integer or half integer. You can see, I will just take one example, that let L is neither be an integer nor be an half integer. Suppose I say L is 0.4. So, what will be L minus 1? So, 0.4 minus 1, that will be minus 0.6, and what will be L minus 2? that will be minus 1.6, L minus 3 will be minus 2.6 and so on and so forth. In this series, when you see that I started with plus L, minus L would have been minus 0.4. So, in this series starting from 0.4, I can never reach minus 0.4 when I go in the step of 1. So, therefore, 0.4 is not an acceptable value for L. What is an acceptable value? If it is an integer or is a half integer, then it is all right. So, for example, if it is an integer as 2, then in the step of 1, so 2 minus 1 is 1, 0, minus 1, minus 2. So, here I see that plus L, minus L both are present, and this is the maximum value of beta and this is the minimum value of beta, and they are all in the step of 1. Similarly, when I take 1.5, which is half integer, the next one will be 0.5, the next one would be minus 0.5, minus 1.5. Again, I have L and minus L both in this series, and the series is in the step of 1. So, in today's lecture, we discussed some important property of the eigenfunction of L square and Lz operator. We said that since Lx, Ly, Ly, Lz, Lx, Lz, they do not commute with each other. So, therefore, we can find simultaneous eigenfunctions of L square and Lz operator. We will continue our discussion in the next class. Thank you for your attention.